Welcome to Vectors 5. This chapter is about intersection between lines and planes. We'll learn the basics in here, chapter 1 to 3, and we also learn how to find equations of lines and planes. So do make sure that you really understand how to find equations of lines and plane before coming to this chapter. If you need to, please review the lecture recordings. So let's jump straight into it. First, we talk about intersection between two straight lines. Now, if you look at 2D, it's very simple. All right. In 2D, two different lines are either intersecting or parallel. That means let's take a look at 2D. This is 2D, yeah. And either parallel, two lines are parallel, or intersecting. They are non-parallel, they intersect at a point. Now, we think, is it the case in 3D? Now, before that, let us recall, this is the line equation, right? This is a line equation. R, let's recall what R stands for. R is the position vector of any point on the line. So you sub different lambda, you will get different position vector. Now, U is actually the direction vector. I think it's easier if we look at an example. Let's say if R equals to 0, 1, 0 plus lambda 1, 1, 1. Now we always write lambda belonging to red. Now this just means that 0, 1, 0 is the position vector of a point A, and this vector 1, 1, 1 is the direction vector. So this 1, 1, 1 is parallel to the line. Recall? Yes? Now, let us suppose in 3D, now, two lines, L1 and L2, have equations this and this, where U is the direction vector of L1, V is the direction vector of L2. We observe that there are actually four possibilities. I repeat, four possibilities here. First one, I think it's quite obvious. Now, intersecting lines. Now, if you see, if you have two vectors in space, you can actually, look at me, up here, two pens, they can intersect at a point. It's 3D, yeah, it's 3D. So it's quite obvious, they are intersecting. So, when they intersect, they obviously intersect at a point P. Yes, they intersect at a point P. Let's give a quick example. First, example 1a. Show that L1 and L2 intersect and find the position vector of the point of intersection where L1 and L2 has these two equations. I think it's easier if we have numbers, then we can actually see how it works. Look. If they intersect, that means the position vector, if they intersect at a point P, for example, the point P, the position vector, must satisfy both equations. Agree? So what we do is we equate, this is the position vector of any point on L1, this is the position vector of any point on L2. We put them together, we solve, you realize that you can solve them because there are only two unknowns, lambda and mu, but you actually have three equations, right? Two unknowns, three equations. Can we solve? Of course we can solve. In fact, you just need two equations to solve. So if you look at the steps, you can solve using just 1 and 2, all right? And quite easily you get mu equals to 1, lambda equals to negative 2. Now, what about the third equation? Now I want to emphasize this step is very important. Right, this one I'm going to write is super important. What we have just shown is that, let's move my cursor here, lambda and mu actually satisfy equation 1 and equation 2. We have not considered equation 3 at all. So we need to do this. we need to substitute mu equals to 1, lambda equals to minus 2 into equation 3. How do we do that? You look at equation 3, the left hand side of 3 equals to 3 minus 2 equals to 1. I think quite easy. What about right hand side of 3? I'll get minus 1 plus 2 times 1. I also get 1. What does this tell me? This tells me that this solution set here now satisfy equation 1, equation 2, and equation 3 now. This is to check whether it satisfy equation 3 too. It is super important here, look here, to check that there's a unique solution that satisfies all 3 equations. What does it tell us? If you look here, it just tells us that the xyz component, you can find a unique lambda and mu that satisfies the xyz component. Then we can say for sure this point lies on both L1 and L2. So we can see now L1 and L2 are intersecting lines. Then you can either substitute your lambda or your mu, either one. Alright, in this case we substituted into your mu here. Mu is 1, alright, into your equation line 2. Alright, yes, then you get the position vector. Yep. Alright, now let's take a look at example 1b. Find the position vector of a point of intersection in L1 and L2 in example 1a. Now, there is slight difference. Read the question super carefully. The question only say find. You just need to find without having to check whether 3 equations are satisfied, because the question already tell you that it's actually a position vector. You don't need to prove anything. So all you need to do is to solve L1 and L2, put them together, just find a mu, and we are done. So there's a slight difference between example 1a and example 1b.